What do we do if we're looking at functions that aren't continuous anymore? Well, hopefully they're piecewise continuous. If we can cut them into pieces and each piece is continuous, that's what we're going to do. And if they're not even piecewise continuous, we're just not going to bother. So that's going to be our first step. Split into continuous pieces, if necessary. And then the second is, as things go off to infinity, if necessary, use limits. Use limits if the function approaches, and potentially one-sided limits. Use one-sided limits if the function approaches positive or negative infinity. And again, if necessary. Sometimes you'll have to use one. Sometimes you'll have to use both. Let's see what this looks like in action. Example 4. All right, so the integral of 0 to 4 of 1 over the square root of 4 minus x dx. So this is continuous on the open interval from 0 to 4, but it's not defined at x equals 4. And we've sort of cheated a little bit with integrals like this. Cheating won't work in example 5. Cheating will work in example 4. So let's just get into the good habit, do something that will always work and not cheat. So here's how we do this. Again, we don't have to do part 1 here. We don't have to do step 1 because this is already continuous on the open interval from 0 to 4. But because the function is approaching positive infinity as x approaches 4, and again, graphically what this looks like, an asymptote at 4, and x is 0, or like here, and then we shoot off to infinity and we're looking at this blue area. Again, we're going off to infinity, we need a limit. And specifically, we need a one-sided limit because we're only approaching 4 from the left. So, again, the book has full formulas. I like to try to explain these away instead of just using formulas that we copy. But if you like those formulas, if you benefit from those formulas, feel free to look them up in the book. Okay? So this is going to be the limit from 0 up to some a as a gets close to 4 from the left. One-sided limits. Okay? Because this function's not even defined at 4. We can't plug in 4 necessarily. Turns out here we can cheat and we actually could get away with it. But in general, you're not always going to be able to do this. So that's what this step 2 means. Okay, this blue 2. Use one-sided limits if the function goes to either positive or negative infinity. And it does here. So we're going to write it in this form. Square root of 4 minus x dx. Now we evaluate this with a u sub. You got to be careful with your u sub here. Let u be 4 minus x. Then du is negative dx. So we need a negative dx. Let's compensate by adding a negative in front of everything. And then if x was equal to 0, what is u equal to? 4 minus 0. If x is equal to a, what is u equal to? 4 minus a. So that gives us negative limit as a goes to 4 from the left of the integral now from 4 up to 4 minus a. And this becomes 1 over the square root of u, which is u to the negative 1/2. And this becomes our du. Well, that was not. And now we can just evaluate it, no problem. Negative limit as a goes to 4 from the left of the antiderivative, add an exponent, divide by that exponent. Dividing by 1/2 is the same as multiplying by 2. Evaluated from 4 to 4 minus a. Well, we can factor out the 2 if we'd like. We're just left with the square root of u at 4 minus a minus the square root of u at 4. Well, square root of 4 is just 2. That's nice. What's the other guy doing? Well, this is a continuous function. As a gets close to 4 from the left, what happens here? As a gets really close to 4, this is going to 0. And it really matters that it's going to 4 from the left. This limit does not exist as a approaches 4 from the right. Right? A approaching 4 from the right would be like a equals 4.1, then a equals 4.01, then a equals 4.001, etc. But at all of these values, this is not, it doesn't even exist. Well, it's imaginary. So this limit can be evaluated, and we're just left with negative 2 times negative 2. This area is 4. And again, you could check your answer with Desmos. Let's do another one. Integral from 0 to 2 of x times the natural log of x dx. Okay, so is this continuous? It's continuous on the open interval from 0 to 2, but it's not defined when x is equal to 0. We're going to set this up with methods for improper integrals. This is going to be the limit as a goes to 0 from the right, because we're looking from 0 to 2. We have to always approach from inside the interval. Okay, so here, we were trying to get to 4. How do we approach 4? We have to approach 4 from the interval. So we have to approach 4 from the left. Here, we're looking at the not here. Here, we're looking at the interval from 0 to 2. We can't touch 0, but we can approach 0 from the inside of the interval. We can approach 0 from the right. Integral from a to 2 of x ln x dx. Let's go off to the side and calculate this antiderivative. Normally, this is our u. We're going to need integration by parts here. A u substitution won't really help us. But we don't want this to be our dv. So let's let this be our u. U is usually the thing that's easy to differentiate. And dv is usually the thing that's easy to integrate. X we can do either with. So we'll let our decision be based on natural log of x being easy to differentiate. So that means u is x, du is dx. dv, whoa, that's not what that means. That means u is natural log of x, so du is 1 over x dx. dv is x, so its antiderivative is v, 1/2 x squared. Now integration by parts says the antiderivative of u times dv is equal to u times v minus the integral of v du. And now we can evaluate this and simplify. So we get x ln x minus 1/2 integral of just x dx. That's x ln x minus 1/4 now, because the x squared, plus c. Add a power, divide by the power. So this is going to be the limit as a goes to 0 from the right of the integral. We already evaluated the antiderivative, x ln x minus 1/4 x squared. We don't need the plus c. It's a definite integral from a to 2. Plug in 2, plug in a, evaluate the limit. Limit as a goes to 0, from the right. At 2, it's 2 ln 2 minus 1/2 2 squared. And at a ln a minus 1/4 a squared. So as a is going to 0, this guy is easy. If a is going to 0 from the right, a squared is going to 0. Great. What about this guy? A is going to 0, but the natural log is going off to negative infinity. Right, remember natural log looks like this. Because the input of natural log goes to 0 from the right, the output is going off to negative infinity. This is 0 times infinity, an indeterminate form. We have to use L'Hopital's rule. So let's do that on the next page. The limit is a goes to 0 from the right of a ln a. Sometimes people are more comfortable looking at these limits with x's. So when we go off to the side, we can't have x's here because x means something else. But if we go off to the side, yeah, we can look at it for x's and then we could just say it's the same for a's. So again, this is that 0 times infinity case. To use L'Hopital's rule, we have to write this as either infinity over infinity or 0 over 0. So we're going to write this as one of two things. Either we're going to put one of these on the top and one of these on the bottom. We could write this as ln x over 1 over x. Or we could write this as x divided by 1 over ln x. That's what we always do when it's this form. Put one of them in the bottom. And again, it's the same because dividing by 1 over x is the same as multiplying by x. Dividing by 1 over natural log is the same as multiplying by natural log. And now this puts it in the right form, either infinity over infinity in the case of the first, or 0 over 0 in the case of the second. But we're going to have to use L'Hopital's rule. We're going to have to take the derivative of the top and the bottom. Which top do you want to take the derivative of? They're both easy. Which bottom do you want to take the derivative of? The guy on the left is easier than the guy on the right. Guy on the right needs chain rule. So let's, again, you can choose one. We're going to choose the one on the left. And now again, as x is going to 0 from the right, this guy, the top, is negative infinity. The bottom is positive infinity. Oh, this is our right form. Now we can use L'Hopital's rule. We can take the derivative of the top, which is 1 over x. We can take the derivative of the bottom, which is negative 1 over x squared. And now we can evaluate this limit. Let's simplify. This is 1 over x divided by negative 1 over x squared. Dividing is the same as multiplying by the reciprocal. So it's negative x squared over x. What is negative x squared over x? Negative x. Now we can evaluate this limit. This whole limit is 0. So even though it's an indeterminate form here, we use L'Hopital's rule to show that it is truly 0. Okay. That gives us our answer. Whatever this first guy is, 2 ln 2 minus 1/4 times 4. That's our answer. Should be able to use Desmos to check. Integral from 0 to 2 of x ln x dx. Is that 2 ln 2 minus 1? I think so. Easy as 1, 2, 3. We'll do another one of these in the next video. Let me know if you have any questions, and good luck.